So welcome to the next topic, alcohols and carboxylic acids, and we'll also have a little look at a derivative of carboxylic acids called esters later in the topic. So these are the learning objectives for the lesson. Okay, so we're basically going to go through three different organic groups, alcohols, acids, and esters, which are all kind of interlinked to each other anyway. So you'll have to know the functional groups for each of those, the reactions of each of those, the manufacture of each of those, and what they are used for. So the first group of organic molecules we're going to look at is the alcohols, okay? And here they are here, okay? So I've given you the name, you basically have to know the names of the first five. I've given you a bonus one, hexanol. So why do they have these particular names? Well, if you look closely at their names, the meth, eth, prop, and but part count for the number of carbon atoms. Okay, so for example, meth, 1 carbon, eth, 2 carbons, pro, 3 carbons, etc. The and part tells you the molecules are saturated. So what does that mean? Well, it means that because carbons in group 4, it can form a maximum of 4 bonds to it. Okay, so it says it's saturated. This is without double bonds or triple bonds, for example. And the ol part is a reflection of the functional group. Okay, all alcohols have this OH functional group. You can also see for numbers greater than 2 for number of carbons as you go down, that they can also be seen as propan 1-ol, okay, or butan 1-ol. What does the 1 mean? Well, it means that it's on the first carbon here, okay? So basically for this particular topic, we're only focusing on the 1-ols, okay? We're not going to move around and have, say, propan 2-ol. It's going to be the straight chain alcohols. And we're primarily going to focus on the guy highlighted in blue, ethanol, here.
There's a great demand for alcohols in industry. We use them to make antifreeze for our engines and for antiseptics to disinfect the skin. If you've ever used a hand sanitizer that works without water, that will have contained an alcohol. We also used a 2-carbon alcohol, ethanol, as an ingredient in alcoholic drinks. The alcoholic drinks industry is huge, and making beer or wine requires science. The process for making alcoholic drinks is called fermentation. The reactant in fermentation is sugar. It comes from natural plant extracts, barley in beer making, and grapes in wine making. These sugars have the general molecular formula C6H12O6. Fermentation converts them into ethanol and carbon dioxide. You might notice this equation isn't balanced yet, so have a go as a mini challenge. Pause and continue when ready. Here's the answer. The problem is, this reaction happens far too slowly to be of use to industry, but it can be catalysed by the enzymes of a naturally occurring fungus called yeast. Let's move on to our second route. This one also makes ethanol, this time from a hydrocarbon called ethene. You might have come across it in our videos on hydrocarbon cracking. Here's the ethene molecule and its molecular formula. Here's the ethanol molecule from before. Now look at the numbers of each atom on both sides. Can you think of a very common molecule we can add to ethene to produce ethanol? Again, pause and think, then resume. Well, the answer is the good old water molecule. It's reacted with the ethene in steam form, and the ethene double bond breaks open, allowing addition of H2O. Phosphoric acid is used as a catalyst. Note that ethanol is the only product in this reaction. The ethene route is faster and more efficient as there is no waste product formed, only the useful one. Fermentation also yields carbon dioxide, which isn't useful to us. But ethene is cracked from crude oil, which is a non-renewable resource, so we won't be able to carry on acquiring it this way forever. Plant sugars, on the other hand, are a renewable resource. The ethene route also requires much more energy. The initial crude oil must be heated to a high temperature, and so too does the water to create steam. The fermentation route requires heating only to 37 degrees.
So the first thing we have to discuss is how we make ethanol. So the first way is, because we're studying chemistry, a chemical method. So it's made by the addition of water to ethene's double bond. So you would have looked at alkenes earlier in the course. Okay, so this is how it's made. You've basically got ethene coming along, reacting with water with a phosphoric acid catalyst, so in small amounts. Okay, it acts as the catalyst, speeds up the reaction because the reaction actually requires quite forcing conditions. It's done at 300 degrees Celsius and at 60 atmospheres of pressure. So quite high pressure, quite high temperature. So the other way that ethanol can be made is biologically, okay, through the fermentation of sugars, making alcohols, okay. So that's why maybe your pineapple tastes a bit funny, because probably the sugars in the pineapple are being fermented into alcohol. So fermentation occurs without oxygen, okay, and this is the equation. So basically glucose in a fruit, for example, or any basically plant material, gets broken down into ethanol and carbon dioxide. And it happens around 37 degrees Celsius, about body temperature. And this is an industrial plant where it's happening. So you can make lots of ethanol for industry this way when you have lots of cane sugar, for example. This is what Brazil does. It uses ethanol as a fuel source rather than petroleum by using the cane sugar it has to make ethanol fuel. So enzymes in a material called yeast, okay, so that's kind of a life form, which is all around us, is used to catalyze the reaction. That's how we make beer, for example. And this explains, the use of the yeast explains the reaction conditions that are actually used. Okay. So in air, yeast produces carbon dioxide, so when there's enough oxygen around, it produces carbon dioxide. We don't want that, we want it to produce ethanol, so what you do is you take the oxygen away, and it starts to produce ethanol. And if temperatures are too high, say greater than 40 degrees Celsius, then the yeast die off and the enzymes get denatured. Okay, so the enzymes are the kind of the catalysts, they're proteins that catalyze biological reactions. For example, converting glucose into ethanol, and basically the enzymes lose their shape as they heat up and they can no longer be effective, so they're not doing the reaction. Additionally, yeast, being living organisms, die when alcohol levels get too high, just like you would. Okay, so if it gets about 15% alcohol, they die off and the reaction kind of finishes. So what you do is you remove the ethanol through the process of fractional distillation. Okay, this takes advantage of the difference of the boiling point between ethanol and water, where water boils at 100 degrees Celsius, where ethanol boils at around 78 degrees Celsius. So another reaction that ethanol can undergo is oxidation. Okay, so ethanol can be oxidized to form either, well, if it's complete oxidation with combustion, either carbon dioxide and water, or something called ethanoic acid, okay, or vinegar, basically. This is why, for example, this man here is spitting back his wine, because what's happened is the ethanol in the wine has been oxidized, probably by microbes, into vinegar. Okay, so now his wine tastes more vinegary than its sweet, sweet ethanol. Okay, so ethanol can be oxidized in three ways, either through complete combustion, okay, forming carbon dioxide of water and oxygen, through microbes to form vinegar, or chemically by heating with acidified potassium dichromate, which we demonstrated in class today. So in terms of chemical oxidation, it can occur in two ways, most commonly in the laboratory. Alcohols can be oxidized into carboxylic acids, which is this new class of compound, by using acidified permanganate or dichromate. Okay, so permanganate has a very strong purple color, dichromate a very strong orange color. So what happens when the reaction happens is not only are acids formed, but the dichromate ion goes from a nice intense orange color to green. And also, if you use permanganate, it goes from that nice intense purple color, which you're probably very familiar with, to a colorless solution.
Carboxylic acids are found widely in nature. Here are 3 examples. First up, methanoic acid. Methanoic acid is commonly called formic acid, from the Latin for ant, formica, as it is the compound red ants inject into their prey. It was first isolated by distilling red ants. Secondly, ethanoic acid. Ethanoic acid is commonly called acetic acid from the Latin acetum, meaning sour wine. This is because wine, which is a solution of ethanol, is oxidized in the air to ethanoic acid. Vinegar is a dilute solution of ethanoic, acetic acid. Then, ethane dioic acid. Ethane dioic acid, commonly called oxalic acid, is toxic and is found in rhubarb leaves, and that is why we should never eat them. Carboxylic acids contain the carboxyl group, as shown in the video. This is made up of a carbonyl group and a hydroxyl group. Let's have a look at the reactions of carboxylic acids. Carboxylic acids react as typical acids. These are, number 1, acid plus metal goes to salt plus hydrogen. For example, ethanoic acid plus sodium to sodium ethanoate and hydrogen. Number 2, acid and base goes to salt plus water. For example, ethanoic acid and sodium hydroxide become sodium ethanoate and water. And 3, acid plus carbonate go to salt plus carbon dioxide plus water. For example, ethanoic acid and sodium carbonate to sodium ethanoate, carbon dioxide and water. Carboxylic acids also give another important reaction called esterification. Here they react with alcohols to give an ester plus water. An example is ethanoic acid and ethanol to ethyl ethanoate and water. This is a reversible reaction, which can be seen from the directions of the 2 arrows shown. In this reaction, a few drops of concentrated sulfuric acid are added. This sulfuric acid acts as both a catalyst and to remove the water formed, thereby displacing the equilibrium to the right following Le Chatelier's principle. If you don't know this principle yet, no problem. We have a video about it right here just for you. Now, let's take a look at what esters are actually used for. Esters have characteristic smells and are responsible for the flavour of foods and smell of flowers. They are therefore useful as flavourings and perfumes. Some examples of esters, together with their smells, are 3-methyl-butyl ethanoate, or bananas, pentyl ethanoate, pears, and octyl ethanoate, oranges. Animal fats, vegetable fats and oils are esters of long-chain fatty acids and glycerol. A soap is a salt of a fatty acid. Check out our water and soap video. So, to recap, carboxylic acids contain the carboxyl group. They show the typical reactions of acid, With alcohols, they undergo esterification to produce esters, and esters are used in the catering and cosmetic industries.
So that now brings us to the carboxylic acids. Okay. And these are the carboxylic acids here. So you have to know the top 6 carboxylic acids, their names. So again, the meth part says there's 1 carbon, the F 2 carbons, the pro part 3 carbons, etc. And now we've got the anoic part, which says, well, says again it's saturated. So again, the carbon here is saturated if we're looking at ethanoic acid. So it's got 4 bonds to carbon. And the oic parts, well, this is the functional group here, the C double bond O, single bond OH. That's the functional group of the carboxylic acid. So you have to know the names of the first 5, giving you a bonus with the 6th one. Additionally, their structural formula here, and also you have to know their displayed formula. Okay, so those are the 3 things you basically have to know when it comes to the structure. Okay. So carboxylic acids can also react just like normal acids, except they react a bit slower. Okay, and you'll learn the reasons why they react a bit slower if you continue on with A-level or IB chemistry. Okay, so previously in the course you would have seen that acids react with metals to form hydrogen gas and salts. It's the same with carboxylic acids. So carboxylic acids react with metals to form a salt and hydrogen gas. And that's the example there. So you've got a carboxylic acid where this R group here can be either a methyl group, etc. Okay, propyl group, butyl group. And it reacts with a metal, in this case magnesium, to form a salt. Okay, so if it was an ethanoic acid, it would form magnesium ethoxylate and hydrogen gas, which you can test, of course, with a lighted splint and the pop test. Okay, so there's an example there. Ethanoic acid reacting with magnesium to form magnesium ethanoate and hydrogen. And also, just like a normal acid, they react with metal carbonates to form a salt, water, and carbon dioxide gas. So again, ethanoic acid reacting with sodium carbonate forms sodium ethanoate, water, and carbon dioxide is given off, which of course turns lime water cloudy, so you know you've got carbon dioxide. So those are the kind of examples of carboxylic reactions. So other metals, not just magnesium, behave as you would expect. Sodium, of course, would be dangerously reactive. Zinc produces bubbles of hydrogen more slowly because it's lower down the reactivity series, whereas something like gold or lead probably won't react because it's quite low on the reactivity series. So this is what we've got now. So you would have previously learned about alkanes and alkenes. Okay, you now have a general formula for them and an example and the functional group. Okay, and now we've added alcohols and carboxylic acids. Okay, so the functional group of an alcohol is an OH and the carboxylic acid is COOH. Okay, so now we're just building up this list of organic molecules you've now become familiar with. So to continue on with that, ethanol and ethanoic acid can react to form something called an ester. Okay, so esters, they usually smell very nice. They're used in food colorings and also in perfumes. Okay, quite common. They're also very commonly used as solvents because of their volatility. They turn into vapor quite easily. And the typical smells can be bananas, raspberries, pears, but they can also smell a bit like goat and vomit, depending on the alcohol or the acid that you use. Okay, so essentially what happens is you've got an alcohol, a carboxylic acid, they form the ester with water. But you need to also use an acid catalyst to speed up the reaction, and maybe slightly warming temperature, about 40-50 degrees. But we'll work on that as an experiment in class. So this is an example of the ester. Okay, so the functional group for the ester is going to be COOC. Okay, right in the middle here, this highlighted by this green point. And in terms of naming esters, the ethyl part comes from the alcohol, so the first part comes from the alcohol, and the ethanoate part, the second part of the name, comes from the associated acid. So just to finish off, let's look at some naming of some esters. Okay, so just a little hint. When working out the alcohol and the carboxylic acid an ester comes from, the YL part tells you the alcohol and the O8 part will tell you the carboxylic acid. So as illustrated by the table here, so propyl ethanoate is made up of propanol and ethanoic acid. Okay. So basically the colors here illustrate on the table that the red comes from the alcohols and the black part comes from the carboxylic acid. You would also need to be able to reverse this and work out which carboxylic acid and alcohol you would expect to react together to produce a given ester. So that's basically what this table allows you to do. You basically break apart the molecule between the carbon and oxygen and an OH to one side and a hydrogen to the other. So then you have two OH groups. Okay, so for this one here, for example, just break it in two. So methyl would come from the methanol, and the methanoate would also come from methanoic acid. Okay, that's pretty much all you really need to know about these three functional groups and these three organic chemistry groups. And next lesson we'll be moving on to the final topic, which is polymers.